Hi, so this is a little video on the transform and conquer design technique for algorithms. So this is a very natural idea that when you're faced with a problem, you just represent it in a different way somehow that makes clear what the solution is. So we'll do a few warm-up examples of this, and then we'll tackle our serious examples. So the first little warm-up example is element uniqueness. So if you're given some numbers, a1, a2, up to an, and you want to ask the question, are any two the same? So the obvious way to do that is to compare a1 to a2, and then a1 to a3, and then ... and finally compare a1 to an. And if none of those are the same, then you could leap in and compare a2 to a3 and a4 and up to an and so on. So this could be a double nested for loop, and this obvious algorithm takes theta of n squared steps. If you count up all the comparisons you're actually doing. But the transform it first, and this is always, when you have any collection of numbers, this is probably always a good idea to think about, is you pre-sort them. After we pre-sort them, they're in a completely different order, so that's transforming the list. And then you see if any two neighbors are the same. And that, of course, takes theta of n to do that. So the pre-sorting becomes the hard part. All the work takes n log n if you use a decent sorting algorithm. And then you do theta of n. So, of course, the theta of n work is negligible, and it's an n log n, which is vastly superior for large n to the obvious algorithm. So that's one little example of this pre-sorting idea. Another example is evaluate a polynomial. So if we have a polynomial like p of x is equal to, I'll use the same one that's in the notes, 3 plus 7x plus, minus 4x squared, I'm trying to find it here, plus 5x cubed. So if you evaluate that in the ordinary way, like if you want to take p of 9, the normal human way to think about that is to say, well, it's 3 plus 63 minus 4 times 81 plus 5 times, then we'd have to maybe calculate 9 cubed, which, I don't know, maybe is 729, I think. And then we'd have to go back and do some of these and combine them and all this. And actually that approach is in theta of n squared, where n is the degree of the polynomial. But it's also a really silly way to evaluate a polynomial. Instead, we should transform the polynomial and write it as 5 times x minus 4 times x plus 7 times x plus 3. And now you can just say it's 5 times 9 is 45, minus 4 is 44, 41, and times that by 9. On the calculator, this works great. You get 369, and then add 7, multiply by 9, and then add 3. Anyway, this approach is theta of n, and it's also much better for calculator use because you don't have to have any extra storage. So those are two little examples. Now we're ready to tackle one that's like super famous and useful in mathematics. What's going on now? Okay. So this next problem is solve a linear system. And you're totally familiar with this, but I'm going to repeat it to remind you of it anyway. You may find this extremely trivial and boring, but I want to remind you of some of the things you might have learned, hopefully learned in Math 2140 or the equivalent. So if someone says to solve the system 2x plus 3y minus z equals 6, 4x plus 7y minus 5x equals 5z equals 3, and minus 6x plus 11y minus 4z equals 4. So that's an instance of the linear systems problem. So you're totally familiar with this. And way back in your early math classes, you might have learned one way to do this, which is to add multiples. For example, we might subtract twice this equation from this equation, and that would get rid of the x term. And then we could we could add 3 times this equation to this equation to get rid of the x, to get another pair of equations just involving y and z, and so on. But all that turns out to be kind of a silly way, so instead before we do those sorts of steps, a really huge idea in mathematics was to just pull away the coefficients. So this is a mild transformation of the problem, a kind of trivial one, but really useful in practical terms, I guess just kind of obvious. Okay, and so there's an imaginary, this is the so-called augmented matrix form of a system of linear equations, but that's just a trivial transformation. Now we do row operations on this system, and we transform what the different equations, what these 3 equations are saying. And at the end, we'll have them written in an equivalent form that has exactly the same set of solutions as these original equations, but it's much easier to see what the solution is. So I'm assuming you're totally familiar with this. So embedded exercise 27, I guess I'll now do it, 37, although it's going to be slightly painful. So the first step is to add twice minus 2 times the first row to the second row, and I'm going to add 3 times the first row. So the way I like to do this is to just jot in the numbers. So I'm just taking minus 2 times each of the guys in the first row and writing them in small, getting ready to add them on the next step. So minus 2 times 3 is minus 6. Minus 2 times minus 1 is plus 2. Minus 2 times 6 is minus 12. And then on the other row, it's 3 times. So I get 6, 9, minus 3, and 18. So in the next step, this is equivalent to 2, 3, minus 1, 6. And then we get 0, 1, minus 3, minus 9. On the third row, we get 0, 20, minus 7, 18 plus 4 is what, 22? So that's exciting. And now we can, there's various ideas of what we might do here. I'm going to go ahead and use this second row to clean out the other guys. So I'm going to add 20 times this row. Well, first I'm going to add minus 3 times this row. So we get 0, minus 3, and minus 3 times minus 3 is plus 9. Minus 3 times minus 9 is plus 27. And then we're going to add minus 20 times this row. So we get 0, minus 20, 60, 180, which looks horrible. So that's equivalent to 2, 0, 8, 33 maybe. It's so easy to make mistakes on this, so I probably will give up in despair. 0, 0. Okay, now we get 53, and oh no, I've done it badly. 22 plus 180 is 202, I think. Yeah, I probably blew it here. Oh no. So it turns out I didn't do this on the first row. One algorithm says I should have divided that row by by 2, but I didn't because these odd numbers would have given me fractions. But now I can do this deeply exciting fact, which indicates I'm on the right track. I'm just recopying, which is how we spend most of our time doing row operations. It turns out if you divide 53 by 1/4, so I can also divide the row by, multiply the row by a constant 1/4. So, sorry, I'm going to divide it by 53. So I get 1 here, and 202 divided by 53, I hope, is 4. Is that right? Yeah, that's what I was expecting. Because see, I built the right-hand side by plugging in simple numbers for x, y, and z and calculating what you ought to get. Okay, so at this point we know that z equals 4, so that's the big punchline. That if you can transform an equation to look like that, it gives you easy information. And now I can do the same just to be completely rigid about it. I'm going to take 3 times the third row and minus 8 times the third row to the first row. So I get 0, 0, minus 8, and 32, minus 32. And then for this last row, I get 0, oops, wrong way, 0, 0, 3, and 12. So that's equivalent to 2, 0, 0, 1. Uh-oh, did I do that wrong? I think I did. That doesn't seem like what I wanted. 33, so I might have made some mistake here, which is not good. Believe it or not, okay, so if that were really correct, then we'd be done, because we'd know that this z equals 4, y equals 3, and x equals 1/2. So I actually made a mistake somewhere, and you can go back and figure out where that was with your vast knowledge of, oh, I know where it was. It was right here. If you take, right here, I should point. So if you take the, what did I take? I took minus, yeah, I took 3 times, wait, I'm thinking, oh no, I don't know where I'd made the mistake. Okay, anyway, so that's exciting. But you get the idea, and you, presumably in your matrix algebra class or linear algebra class, you learned those things. And I'm just trying to point out here, just to remind you briefly of them. Of course, we're going to use software to do all of these steps. We're never going to lower ourselves to do these by hand in the future. Even we're going to do some very serious work with these. We'll let the computer always do the calculations, so it won't be tedious. So the point here is we start with a system where it's really hard to see the solution, and after transforming it, we get a system where it's really easy to see the solution. Okay. All right. So on the on lesson 10, which we're going to see some other examples. So there'll be 2 exercises asking you to do other examples of the transform and conquer. So I want to take a little more time here to start talking about linear programming and how we're going to use row operations in a really exciting way. Okay, so LP. So LP, linear programming, is a very important problem in computer science. On page 58, I wrote some beautiful comments about it. I think it's just an extremely important problem. So this is the problem, and the algorithm, one algorithm to solve it is a really important and famous algorithm. It's called the simplex method, and it has an interesting history in the study of algorithms. So it turns out, well, we'll talk about all these later, so I don't want to get ahead of myself. So we are going to study 2 algorithms for solving linear programming. We're going to study a brute force algorithm based on some important theory of linear programming, and we're going to study the simplex method, which is an apparently better method, but in fact is really not all that much better probably, except an average. In the average case, it's way better. So it's a really interesting situation, similar to quicksort, where in the worst case, this algorithm is no better than brute force, but in the average case, the vast majority of problems we tackle, it's vastly better, runs vastly faster. So I seriously, when I taught linear programming class in early 80s, like 1983, 4 in there, the book we used said that half the computer time being used on the planet was being used to do the simplex method. And if you look at lists of most important algorithms, the simplex method will be listed almost always in them. Okay, and it's also, linear programming as a problem is very useful, and we're actually going to use it together with branch and bound idea to solve the traveling salesman problem. Versions of the traveling salesman problem that should be too big for us to handle them, and just using our dynamic programming algorithm. So that's kind of where we're going. It's going to take us a while to get there. Okay, so the linear programming problem, LP, which we call LP, is to maximize C1x1 plus up to Cnxn, which we can write as C transpose x if we want to, because C is a little vector that's called C1, C2 down to Cn, and x, so these are called the cost coefficients, and x is called the decision variables, and x is x1, x2 down to xn. So they're in unknowns kind of that we're going to play with. And we want to maximize this quantity subject to, and I shorten that by ST because it takes too long to say it. And then we have a big matrix that's shaped kind of like this called A. So A has rows 1 through M, and we multiply A times X, and A has columns 1 through N, which matches up with X1 through Xn, and that's equal to B1 down to Bm. Okay. So this system, this would be a system of linear equations just to solve that has infinitely many solutions typically. And you may have done that in matrix algebra, where you did some row operations and made some identity columns, and then set the other columns to arbitrary parameter values, and then solve for the others. So that's kind of, we're going to do that sort of thing, but there's something really new here. The new thing is that all the x's are greater than or equal to 0. So it's that constraint that makes this an interesting problem. Otherwise, we'd just be doing something that would have infinitely many solutions, and we'd almost always be able to achieve positive infinity for the objective function. So this is called the objective function. These are called the decision variables. This is called very creatively the right-hand side matrix. This is called the coefficient matrix, and these are called the restrictions. So these guys, just some of the terminology, these equations are called constraints, and the x greater than or equal to 0 are called restrictions. So it's important to realize that the restrictions, they're the only thing in here that's not a strict equality. Okay, and we're also going, yeah, I guess not. Okay, so there's an example in the pre-reading that I'd ask you to look at. It's kind of, and it'd be really helpful if you did actually read it, because it's kind of fun. And the point is, it gives you just one concrete example before we plunge in and do some very serious work with the linear programming. It gives you one simple little example. So I don't think I want to waste the bytes or the time to go through it, because it's written very beautifully. And I'll just point out that after you've figured out what the problem is, namely to maximize 200x plus 300y, the inequalities, there's actually inequalities. So it turns out the restrictions, so the variables are x and y. It's a little 2 decision variable problem, whereas in general we have n decision variables. And the constraints turn out to look kind of like, you want to look at the nice picture of them. They turn out to look something like this. So the feasible set, this would be a perfect place for the highlighter. Ooh. So the feasible set, it's too big. So the feasible set is all the points xy that lie underneath all of the inequalities, and the winning point is right here. Whoops. So the winning point is right there, but there's other candidate points where all of the lines, so anywhere there's a pair of lines crossing, you get a possible winning solution. So you really should look through this carefully, and we'll in the in-class mini tutorial on using the software, we'll talk about how to solve this at some point in the near future. So we're going to use much more complicated problems than this, but we're not going to go off and make this into some kind of business or operations research or economics class. Even though linear programming is great for all kinds of practical things, like I said before, we're going to use this as a linear programming as a tool to solve the traveling salesman problem. It's not at all obvious how that can be done, and so that'll be fun and exciting. So I think that's all I want to say at this point in this video. Thanks.